So I want to start the morning off by talking a little bit about midterm, plan for that, and to give you just a couple of bullet points here on what we're going to do today. Today we're going to finish off the conversation on trusses with just one more little problem I've already drawn up here on the board. We're going to get that one out of the way, then we'll move on into the study of frames, which puts us in position that by Thursday of this week we'll be studying machines. And machines, of course, we've already seen that when we go back to the early parts of the course where we looked at the can crusher. That was a form of a machine. So we're finally up to that point where we are ready to handle that. So folks, knowing where we're at too also with the semester where it's at, and correct me if I'm wrong, upcoming Monday, right, so a week from today, that's Labor Day, and you guys are not here. Is that correct? Good. Okay. Just want to be sure I got that part down. So, with all that said, we're getting late into the semester. We want to get the midterm under our belt. So, here's the plan. And I've debated whether I want to do this or not all semester. Whether I just want to just do the traditional thing where we just set aside a day and do the midterm here in class, or send it home with you. I'm going to send it home with you. So it just gives us more time. It's also, where we're at right now in the semester, we just don't have a lot of time to fool around and, eat up time and in lecture with that. So what I'm going to do is I'm going to get the midterm written, ready for you, and available to you by Thursday of this week. Now, there are going to be 3 problems on that midterm. One of them, with certainty, will be a machine type problem. And we haven't even seen machines yet. We're going to start that on Thursday, okay? So the other 2 problems, what I'm leaning towards right now, well, let's say this. With absolute certainty, there will be a free body diagram problem, where the entirety of the problem is just going to be, here's something, and I want you to draw complete, no mistakes, free body diagrams. And that's literally it. I don't want you to solve anything. I don't want you to worry about anything beyond just, I want to give you a perfectly right free body diagram. And then the third problem, so free body diagrams, machines problem, and a truss problem. We'll have a truss problem on there. And I think, as I already said when we were together last, whenever we were together last, I guess today's Monday, Thursday, right? The truss problem, I want to be clear on this as I can possibly be. The truss problem will literally say to you, use whatever method you want. So whether you choose to do that truss problem with method of sections, whether you choose to do it with method of joints, I don't care. This is going with that theme of I want you to pick the thing that resonates with you, and I want you to get really good at it. So that's the three types of problems that we're going to have on there. Of course, we're putting trusses under our belts now. Free body diagrams, we should already be in really good shape to do that. So my thinking is, if I put the midterm into your hands on Thursday, then you will have, by the end of the session on Thursday, at least by that time you'll already have exposure to machines problems, and we should be able to work the machine problem on there. However, and here's where things get dicey because of the holiday. Normally, I would say if I give it to you on Thursday, then I want it back the following Thursday. All right? In other words, a week to work on it. The only problem with that is that means we're only going to have one day studying machines before you see the machines problem on the midterm. But folks, I honestly think that's all we need. I really do. Because if we've done this right, then we're already at a point where you really don't need a whole lot of additional info to work machines problems. You've already seen it. You already know it's just writing a collection of free body diagrams and solving each free body diagram by the equations of equilibrium. So there's really not a whole lot to add to that. So I think the way we're going to do this is I'm going to give you make the, you know what? I just thought of something. As I'm saying this to you, just an idea popped in my head. I may make the midterm available to you Wednesday night. meaning that Thursday when we get together, you would have an opportunity to ask any questions you've got about it, get clarifying info and all that kind of stuff. And then that kind of helps us with the fact that we're not here on Monday and makes it more doable to have that back here on Thursday. So yeah, I'm going to do that. I'm going to get that ready and in your hands. Wednesday night, you'll certainly want to make sure to take a look at it before you come in here. So some of the questions that are going to come up about that, the obvious elephant in the room will be, hey, do you mind if we work together on this? Hey, I hope you do. The reason why, folks, is this. And I know that if you just heard a popping sound, you heard other faculty members' heads exploding when they heard me say that. That's what that was. It sounded kind of like a hollow coconut. You understand why. Yeah, no. Anyway, look, folks, this is real simple. Number one, we can wish and shit in our hands all we want, like, hey, wish and shit, which one weighs more? That you wouldn't do that. The reality is that you really should be doing it anyway. Why? Because the people are going to hire you, the people are going to pay you paychecks when we're done with this. They expect you to collaborate. They want you to work together. They want you to develop relationships with people and work together as teams. So fostering that, I don't think is a bad thing. There's the obvious, and I want y'all to hear me. I want y'all, for those of you looking at laptop screens right now, stop looking at the laptop screens. I am here, that is nothing, so stop. Draw in closely when I say this. I want you to work with each other. If you have a deficiency and you don't understand something, learn it. Learn it from the persons you're working with. And if you're the person who understands it and you realize the person you're working with is not understanding it, then step up and help that person learn, right? This is all about learning, right? This is all about coming away with, hear me on this, marketable skills, things that people will pay you for, right? So help each other grow in that way. The thing that people worry about when we have take-home exams is, oh, there's always going to be that scenario where somebody doesn't know up from down or fetch from roll over or something like that, and they just look at what their friend is doing. They don't learn anything, blah, 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 blah. Hear me clearly. And folks, I hope you don't mind if I sound crass when I say this. If you are that stupid that you're going to pay this kind of tuition money and not learn something, there's no way the planet can help you. You are really out of the game. But if you're like, okay, I don't quite get this, I really maybe haven't stepped up and done the work and all that kind of stuff, but I really need to get this because I know it has to do with my future, then okay, take this golden gift of an opportunity to not have to sit here in class and get burned on a midterm. Take this as an opportunity to learn and develop those skills, right? And for those of you that may be that person who's like, yeah, I really know what I'm doing, so the guy working with me, he doesn't, he can just copy my paper. Don't do that. That's what people worry about. And I told you guys at the very beginning of this class, there are things that students do because they're young and immature. There are things that professionals do because they're not. Be a professional. Don't be a child. Be a professional. If you've got deficiencies, fill in the gaps. Use this opportunity to do so, okay? Taking home a midterm in a course like this is it doesn't happen very often. Trust me, folks, I got a lot of my own colleagues that are like, dude, why are you doing that? You shouldn't do it that way. Yeah, I want to do it this way. I'm old enough I can do it if I want to. So I do it my way because I know what I believe is going to help you the most in the long run, but that's only true if you step up and you're the professional, not the person who is not engaged, who is so dumb that you think you can just pay this money, get your degree, and all is going to be good. It is not going to work out for you. Build marketable skills, and this is my belief, and I would help you do that. So you probably didn't think I was going to give you a sermon this morning, but I chose to. But this is what I want to do, and I think this is the right thing to do. But you've got to prove me right in that. Don't prove me wrong. The bad place to be is proving me wrong. This is an ugly place to go to. Now, So the play, again, in your hands by Wednesday night. You're gonna have, in essence, 8 days to work on it. Yes, I know there's a holiday in there, but it's a 1-hour test, okay? It is a 1-hour test. It shouldn't take you that long, honestly, folks. I'm gonna want it back Thursday of next week, so 10 days from today. I think that's roughly what that runs down to. And the question is going to be, it's gonna come up, and I'll bet you're gonna ask me even though I'm gonna tell you this, or some of you will ask me even though I'm gonna tell you this, how to turn it in. There will be no mechanism to turn it in on Blackboard, none whatsoever. I don't want you to email it to me. I want you to come here on Thursday and give me a hard copy of your exam. All right, that's how you're gonna turn it in. If you're not here on Thursday to do that, it will be late, there will be trouble. All right, so that is the play. Now, questions from anybody? Questions? All right. Well, we can talk about that more on Thursday. Let's talk about that problem right there, folks. I want to put an end to, where? Yeah, fire away.
So you said you were going to give it to us on Wednesday, correct?
I'm going to give it to you on Wednesday, yeah.
Okay, so are you going to just be uploading a PDF and then we can put that out on our own?
Yeah, that's a great question. Thank you for it. Yeah, I'm just gonna put it, like, make it available on Blackboard, and then you can just download the PDF, print out a copy of it, go that way. I think it's just the easiest. Okay, it's a good question. Whether, again, any other questions, anybody? It's great to ask them now. Nothing wrong with that.
Would it be fine if we just potentially wrote down, like, did it on my paper, or do you want it to have like a proper printed copy?
I'm not sure I follow the question. You're going to turn in a copy to me on 2 Thursdays, right?
Yes.
So that'll be a printed copy. Yeah. I don't want an electronic copy.
No, I was talking about like doing it in a like that, right? Getting out all of the questions and everything.
Okay. I got you. Yeah, in that case, I don't care. As long as I got a hard copy. Yeah, I don't care. Just with a caveat though. I have had people do that in the past, all right, and it usually works out perfectly fine. There's usually, but this actually goes whether you're using your own copy or whether you're using the document I'm going to give you. Folks, understand this. When I look at the work you did, what I'm going to be assessing is entirely evidence that you understand the fundamentals of how you get the answer, not did you get the answer, okay? It's how you got there. So the challenge that tends to come up, and I will say this is true in less than 5% of the cases, is number one, you're using a method that I don't have a clue. I've actually had people work exams and courses like this one, folks, and they use methods that I never even taught. And then there's the obvious question, like, well, where'd you get that from? Well, I watched a YouTube video. Well, here, let me see if I can give you negative points, not just 0. Let me see if I can take away some from you. I honestly will look for ways to screw you at that point. Like I said, I'm telling you the truth this morning. Why? Because that nothing says, yeah, I'm dumber and shit because I have to go watch a YouTube video versus just learning what you gave us here and what I'm paying for. Okay, do that. By the way, who's taken mechatronics already? Anybody taken mechatronics? Okay. Yeah, I don't know about who taught you mechatronics, but we have a programming section in what I teach in mechatronics, and I've had people write computer programs in mechatronics, and they're using like language that we don't even teach. It's like, dude, seriously, it's not gonna work out well for you. But anyway, but back to your question. The danger becomes you want to make absolutely certain that there's no ambiguity in what you write on the paper versus what was there. So if I got to look at your paper and I can't see the work you're doing and how that correlates back to the diagram, then I don't know how to assess it, right? I mean, I do, but I'm not going to dig and try to figure it out. So the guidance I would give y'all is if you're going to do that, just make sure that you replicate, the problem, that you draw, the graphic of what would otherwise be on the paper, that there's no, I don't want to look at something that doesn't have a picture on it, just starts off with equations, and I got to figure out what does this equation mean with respect to a picture that I don't have. right? So it's just, I want to make sure you got that in your mind. Like I say, that is not usually an issue, but it can sometimes be an issue, folks. It really can. So another fantastic good question. What other fantastic good questions you guys got? Nothing? Okay, fine. We'll talk more. And again, know that on Thursday, I absolutely want you to ask questions about the midterm. Folks, I'm going to be really, really blunt with you when I tell you this. Students who've had me before know me well, know that I really love to answer questions, and they will literally ask questions that might lead you like 90% of the way to how to do the problem, but if you don't ask those questions, I'm not going to answer them. So the point of that is if you're wise, you'll come in here on Thursday and be ready to ask questions about the problems, because I'm more than happy to help you go in the right direction. All right? So be ready to do that. Be ready. So folks, check out that standard truss right there, folks. We see in this truss here the absolutely nothing new. We see a truss comprised of a bunch of 2 force members. We got loaded up here on a couple of the pins here. We got 2.4 kilonewton force pushing down on pin B. We got a 3.2 kilonewton over there on pin C. We have the usual. We got a pin joint here on A. We got a roller there on F. And if we look at the narrative of this problem right here, the narrative goes like this. It's not a really long one, folks. Determine the force in member AE of the loaded truss. So this particular problem asks us nothing more than figuring out the force in that member right there. Now let's go back and just kind of check a few boxes off. If we knew nothing of the method of sections right now, then here's our recipe, here's our play. If we were using the method of joints, then we would say, all right, step number 1, I got to do a free body diagram of this entire truss. I got to solve for the pin forces here at A, and I got to solve for the roller force down here at F. After I've done that, then where would I go from there? Well, probably you would start off with maybe pin F, so you could figure out what the force is right here in this member. And by the way, would this one be a 0 force member? Remember we talked about 0 force members? The answer would be in this case, no it would not. Why? What would be the difference? We've seen this before where we saw that being a 0 force member, yet in this case it would not be. Does anybody see why that wouldn't be a 0 force member? Anybody? What are you thinking?
You said a 0 force member is when you've got basically a straight line and only one other branching line.
Exactly right. Perfect. So check it out, folks. Just imagine free body diagram in your head right here. If I do a free body diagram of that roller, the force is going to be in line with my finger here because it's going to be normal to the contact plane, right? So the force goes like this, and yet this member here is going up on an angle. That's not a straight line. So since it's not a straight line, this cannot be a 0 force member. So if I'm using the method of joints, okay, again, step number 1, I'm figuring out the pin force here, the roller force here. I would probably do a free body of pin F, which is going to tell me the force here in member AF. And then after that, I could do pin A, and that's going to lead me to the one that I want. Doing that right there was a total of 3 free body diagrams and the application of at least 4, if not considerably more actually, at least 5 equations of equilibrium to get me where I want to go. All right, so doable? Absolutely. Method of joints will take us there. It'll get you there every time. But in this case here, folks, here's where the method of sections really helps us out. Method of sections, as a reminder, says that we can cut a complete section out of a truss as long as we don't cut any more than 3 unknown forces. We're going to cut 3 members out of this. We got to completely isolate that, which means we're going to have 2 completely isolated pieces. But we already know we can draw a free body diagram of anything we want. So if we've got a completely isolated piece, we can draw a free body diagram of either the isolated piece over there or the isolated piece over here. Either one's going to work, and they're both going to lead us to the same place. When you look at this one here, we're being asked to figure out, again, the force here in member AE. That's the only thing we want to know here, folks, force in member AE. So I have 1 unknown here, 2 here, a 3rd one right here. This just smacks of use the method of sections on this one, right? The easy place to cut it, right through here like so. So now I'm going to cut this truss just like that. I see again, I have 2 isolated pieces. it's worth noting I could do a free body diagram of this side over here, but if I do that, I'm going to need to have a solution already for the roller force and the pin force here. Otherwise, I got no ability to do a free body diagram of the left-hand side. I want you to think about that and let that soak in. If we merely cut this before we figure out what the reaction forces are, then we would have 1, 2, 3, 4, 5, 6 unknowns and no place to go with those, right? 6 unknowns and 3 equations. So free body diagram on the left-hand side, not the right place to go. If you really truly wanted to do that, you would have to free body diagram the whole truss first and get these things known, but that takes us back to really the method of joints, right? But look at the right-hand side. The right-hand side has known forces on it. 1, 2, 3 forces where we used to be connected to something. We can do that free body diagram all day long and solve it. So look, remember here between point A and point B, let's consider this as being force in member AB. The key to method of sections, folks, is to remember you're always drawing your arrowhead away from the contact point. So here, let's call this force AB. Let's call this one down here, let's call this one AE, because that's the one we're looking for. And now down here we'll have force, how about EF for this one right here. And now that we've got that under our belts, folks, we're almost ready to go ahead and solve this. Now, I want you to notice, I am keeping this here. Why am I keeping this here? Well, because I still got a little bit of work I want to do to get some angles on this, right? I need to have some angles. So, right off the bat, it should be pretty clear that we're going to need to have angles between these two forces right here. Otherwise, we're not going to be able to resolve them into their components. So, as we look at this, the one thing that really needs to jump out at us, folks, is proportionality, right? Proportionality says if this is 2 meters here, this is a straight line here, and this is 1 meter here, then that means this height here, even though it wasn't given to us, that height's got to be 1.5 meters, right? So now, if that's 1.5 meters, and I look, as we've talked about many times in the course, we always look for triangles, right? I see a triangle right here, right, in which I've got a height here. The height of this triangle leg here is 1.5 meters from here to here, which, by the way, that means this little piece down here has got to be 0.5 meters right there. So I got 1.5 meters up here, 0.5 here, and I know this leg here is 2 based on that original dimension right here. So this angle here that I'm going to call alpha, this angle down here that I'll call beta. When we look at what we've got here, folks, the tangent of alpha, which is the opposite over the adjacent leg. So tangent of alpha would be the 1.5 meters over here, divided by the adjacent leg, which is 2. And if we work that backwards, we're going to find that alpha is equal to whatever the heck I got written down over here, about 14, no, wrong one. I may not have it written down. That's kind of cute. Oh, I do. There it is. 36.9 degrees. In fact, let me just, I want to think about something here, folks. Give me 2 seconds. Oh, yeah, it's 36.87 degrees. Do you know why? It's a 3, 4, 5 triangle. So if you divide this by 3, you get 0.5. Divide this by, I don't think of it that way. Multiply by 2. 3, multiply by 2, 4. That makes this 5 right here. So it's 3, 4, 5 triangle. That's always 36.87. I wrote it down as 36.9, but it can go either way. 36.87 is fine, too. All right. There's that one. And then as far as beta goes, beta, folks, is going to be the inverse tangent. I'm actually going to skip ahead to it here, of 0.5 over 2. And that means that beta would be about 14.04 degrees. All right? So now we know what those angles are. With that, I no longer need, I've got everything I need now as far as dimensionality goes. I'm just going to start getting rid of a bunch of stuff here, folks. Cleaning things up, making it look better as we go along. So now, folks, there is our free body diagram. And as we all know, with the free body diagram, as soon as you can say, hey, I've got a complete free body diagram, and by the way, folks, midterm, remember, without that, your free body diagram will be wrong. Okay? Just know that. So make sure you got your coordinate axis system on there as well. now we all know that once we get a free body diagram and we're happy with it, all we gotta do is just go ahead and start doing equations of equilibrium. The always win, never can go wrong play here, folks, would be to just do the standard. So if I sum forces now in the x direction, and I'm, by the way, just so you know, I'm just gonna write the equations. I'm not gonna solve this. I'll tell you what the outcome is in a second. But if I sum forces in the x direction, I'm gonna have minus AB. I'm going to have the x component of AE here. So keep in mind, AE, EF, AB, they're all tending towards negative x. So this would be minus AE times the cosine of 36.87. And then minus EF cosine of 1404. And that's going to be equal to 0. If we sum now forces in the y direction, let's see here, we will have AE sine of 36.87. We will have minus EF sine of 14.04. That's taking care of these two, and then minus 2.4 and minus 3.2. And that's going to be equal to 0. So, you know, if you step back and look at the two equations we got right now, folks, we got two equations, three unknowns. Clearly we can't solve all three of those, so we need to have a moment equation. And now we get to the same, oops, not summing forces, let's make that a moment. Now we get to the same old when it comes to moment equations. That's just where do we pick the right place to take the moment equation? And folks, I can't think of an easier place in this particular diagram right here. I can't think of an easier place to do the moment about than E. If you think about E, I want you to think about all that's going to go away here. AE will not be in that equation. EF will not be in that equation, and that 2.4 right there is not going to be in that equation. This makes this a real simple one here. So if we sum moments about E, with the reminder, as we always will do, that counterclockwise is a positive moment. By the way, folks, I absolutely, again, on the midterm, I will be looking for whether or not you did include that symbology right there. Again, it's just part of what we need to learn. So if I sum moments about E, I see this AB force right here is going to be causing a counterclockwise, therefore it's positive, and we've already asserted that this height here is 1.5. So I've got 1.5 times AB, and then again the 2.4 is not in the picture, none of those are in the picture, but this one over here is. The 3.2 is causing a big clockwise, so it's going to be negative, so minus 3.2 times, in this case, the moment arm. So remember, distance from E over to the line of action of this force down here, line of action going on forever, that distance is the same as that dimension up there, so simply multiplying by 2. Set that equal to 0. Now if you look at what we got, we solve via our moment equation, we solve for AB. Once we know what that is, we can plug it in up here. Now we got two equations that we can solve simultaneously and knock out AE. And folks, I'll just tell you that AE ends up being, I think it's like 5.65. Let me double check that. Yeah, 5.65 kilonewtons in tension. And let's not forget, folks, you got to state whether or not the force, whenever we're dealing with trusses, you got to state whether or not the force is in tension or compression. That's a must. Yes, fire away.
Is that AE or AB?
It is AE in this case. Yep. So thank you for that. I just want clarity. I didn't seek to solve any of these here. I just said, look, if you solve this one, you'll get what AB is. You can plug it in up here, and then you got two equations you can simultaneously solve, and we get to this one here, but that's for AE. So 5.65. Now, takeaway here, folks. Takeaway. Again, method of sections is literally the same thing as the method of joints. It just looks visually different. It's a little bit of a different approach, but it's nothing new. It's if we bought into the idea that we can literally create a free body diagram of anything we want. In this case, we're saying, well, the thing I want to do a free body diagram of is a chunk of the completely isolated truss. I do it in a way that I don't give myself three unknowns. I apply three equations of equilibrium and I'm there. That's the beauty of the method of sections. It makes it much more straightforward to get to. 2 seconds. when we first looked at using the method of joints here, we realized we're no less than 3 free body diagrams and about 5 equations of equilibrium to get there. This was 1 free body diagram, 3 equations, 1 and done. And there is the possibility that we could do this with 1 equation. We'll see that in a minute. You have a question?
Yeah, so I'm a little confused. So I know we're finding the moment around E.
Yeah.
Solving that equation, that's something for AB, is it not? In the moment equation for around E.
You talking about this?
Yeah, yeah.
Yeah. So again, to be clear, I'm not solving the problem.
Okay.
Okay, I'm just telling you, this is, when you do solve the problem, this is what AE is going to be.
Right. Makes sense.
Yep. Now, I mentioned we could do this with 1 equation, right? Think about this, folks. If I wanted to do this with 1 equation, what would that look like? Well, you got to look at your unknowns, and remember, we saw an example of this. We saw an example of this the other day. Just give me a second here to think about this. We saw an example of this the other day where the strategy was to use 1 moment equation such that that moment equation eliminated the forces that we didn't want to include. So I would love to have 1 equation here with 1 unknown where the only unknown is AE. I would have EF gone, AB gone. Where would I put that point? The answer is I would need to extend the lines of action of those 2 forces in a way that I eliminate, or I find a single point where their lines of action coincide. Now, as I step back here, boy, do I realize I sure did miss this line here. Let me try to just do it a little bit better here, folks, because that's so bad. I don't want you to look at it that way. You try it just ever so slightly differently here. Yeah, maybe that looks a little bit better. Okay, hopefully that's better. Now, this is a very doable thing. The key, folks, the key here is to realize the distances. So in this case here, remember, we used to have a pin over here. There used to be 2 meters right here, and then there was 2 meters here. So we had 4 meters to take us down, the original height here of 2, to take us down to 1. So if I think of similar triangles, I realize this here has to be another 4 meters right here. So if that's 4 meters right there, now if you think about this, I can write 1 moment equation. So if I sum my moments now about this point over here, which I never gave it a name, let's call it point O. If I sum my moments about point O, again, remind myself that counterclockwise is positive. I'm going to have that 3.2 kilonewton force over there doing a counterclockwise about point O, so it's going to be positive. So I'm going to have 3.2 times 4. The moment arm here is going to be 4. I'll have the 2.4 right here, also counterclockwise. So it's going to be plus 2.4 multiplied in this case by 6, so 2 here and another 4. And EF's not in the picture, B is not in the picture, but I'll have AE. So if I resolve my force AE here, so this one's going to be AE cosine 36.87. This one here is going to be AE sine of 36.87. And in doing that now I get rid of this, I don't need this force anymore because I've resolved it now into 2 different components. So if I look at this one here with respect to point O, this one's doing a big clockwise around that, so that's going to be minus AE sine 36.87 times the moment arm. So from this line of action all the way over to O is also 6 again. And then lastly, this force right here, if we slide it way back over here, it's going to be easier to see. If I slide that AE cosine 36.87 here, that one's also doing it clockwise, so it's going to be negative. So I'm going to have minus AE cosine 36.87 times its moment arm, folks, which will just be this distance right here, which is 1.5. And I can set that equal to 0. And there I have 1 equation with 1 unknown, and I'm not going to work it out, but I'm going to bet you anything that if we did, we're going to come up with the same 5.65 kilonewtons. And it would be clear here, when I take the AE terms to the other side of the equal sign, they're going to be 0, so it's definitely going to come out in tension here, just like that. So, even further strengthening our value in the method of sections is the realization that in most of these cases we're going to be able to find that 1 free body diagram And if we're only looking for one unknown, one free body diagram and one equation gets us there. So it's a much more efficient, direct way of doing it. What questions have you guys got about that, or trusses in general, method of joints, method of sections, anything, anybody, before we sunset this one? Yes, fire away. Great question. So the most direct answer is when you've answered the problem, you've answered the problem, right? So if you got, like this one here, for example, which only asked us for AE, there'd be no need to solve for any of the other ones unless you just have to. Good question. What other questions you guys got? Anything, anybody? Yeah, fire away.
The four meters and the 6 meters. Where'd you get that?
So I'm gonna kind of redraw what's no longer here. Okay.
Oh, okay.
So there used to be a piece here that had a pin joint. There used to be a piece down here that had a wheel, right?
Mm-hmm.
So this original distance here was 2 meters.
Oh.
And this height here was 2. So if you think of similar triangles, right? It took us 4 meters to cut the 2 in half, and now I need, or to take away 1 meter from 2, and now I need to take away that 1 meter. So if it took me 4 meters to go from 2 to 1, it's going to take me 4 more meters to go from 1 to 0.
Okay.
And that's where that 4 came in, and then I'm using similar triangles again. So 1 here, 1.5, and so on like that.
All right.
It's
Thank
good,
you.
Good question. Other questions? Anybody? All right, good. So that's the end of trusses. And I know I'm beating a dead horse when I say this, but folks, if there's any takeaway at all in trusses, it should be this, that it doesn't matter what the structure is, what we call it a truss, who cares? The takeaway is the way to solve for the forces in the, whatever it is, the structure, is to draw free body diagrams and apply equations of equilibrium. That's never going to change. That just is the thing. That's the takeaway here. The skill, of course, is in knowing how to do those free body diagrams. And this brings us now to the second half of chapter 4, which is dedicated to frames and machines. And I've already talked about the distinctions between these two. And once again, I hope we all just realize that it doesn't matter what we call them. If you want to call them a frame, if you want to call them a machine, it's like whatever. It doesn't matter. Solving these things is still, again, the same recipe. Equations of equilibrium, or I'm sorry, free body diagrams and equations of equilibrium, right? By any other name, it's not going to change. The distinction, though, just to make sure that we all know what it is a frame is a collection of mechanical elements that by the way it is connected, it can maintain its own shape. That's a frame. A machine, on the other hand, is a collection of mechanical elements that by the way they're connected, doesn't maintain its own shape. The great example is, we all know what a pair of channel locks is, a pair of channel lock pliers, right? If I had a pair of channel lock pliers and I had it held exactly a certain way, and then I decided to toss it up in the air and it's going to land out there somewhere with you all on the ground. Nobody in this room believes that thing's going to have the same shape when it hits the ground as it did when it left my hand. That's a machine. That's it. That is the entire distinction between these two. Machines don't maintain their own shape. That's literally it. As far as working them, though, problem-wise, man, there's nothing here I can tell you, folks. In fact, I want you all to be clear about something. If I've done my job so far, and if you've held up your end of the bargain so far, we don't need to talk about this because you literally already know everything you're ever going to need to know to solve frames and solve machines. You know it right now. There's nothing to lecture about. There's nothing new I'm going to tell you. We just jump on in and say, all right, how about this problem here? So let's do that. I want to show you an example of a frame problem. And let me get it drawn up here first, and then we'll come back and solve it. Okay, folks, in this one here, I chose to write the narrative up here because I want to make sure everybody is seeing and hearing the narrative. I think this is going to be important. So the frame that you see right here comprises two structural elements pinned together with a weight hanging over here from pin A. The narrative of the problem is exactly as it was given to us in the book right here, and that is to determine the magnitude of the pin reactions at B and C if W equals 2,400 pounds. Now, let's unpack a few things here. First of all, we've seen an awful lot of problems so far in the course where we were told something was hanging over here like this, and we were told it has a mass of a certain number of kilograms. And in the case of that mass, we had to multiply that by the gravitational constant to turn that into a weight. But in this case here, we're already given the weight. The weight of 2,400 pounds is the weight. It's not the mass. Pounds are units of force in this in our usage right here, folks. So the mistake that's just waiting for you to make it is you see the 2,400 and you think, I've seen this before. I've watched this movie, and you multiply that by 9.81. Well, two issues with that. You just use the SI units for one and the English units on other. Maybe you're thinking, they're not going to get me on this one, so you multiply it by the English version of the gravitational constant. But even then, you've made a mistake because it's already in units of force. So when you see something given to you in pounds, don't change a thing. The force that's hanging off of point A right here is 2,400 pounds. And then there is as it's stated here, determine the magnitude of the pin reactions. The magnitude of the pin reactions. Now, look folks, we all know that pins have an X force and a Y force, or at least they generally have an X force and a Y force. We're used to reporting answers or solving things in terms of, well, AX equals this and AY equals that, I'm done. Right? But this is saying the magnitude. Well, what does that mean? Well, all it's saying is if you know what the X component is and you know what the Y component is, you've got to combine those into a single force and state what its magnitude is. So we're using Pythagorean's theorem in this case right here. We've seen it. We did that all the way back to chapter 1 actually, folks. But now we're kind of circling back and doing that again. But folks, with that said, here again is where we could just stop right here and say, all right, you already know how to do this, just go do this, right? So you're being asked to figure out the forces, the magnitude of forces right here at pin C, and also right here at pin B. Think about this. You already know that you're going to need to draw a free body diagram of something, and you know that every option's on the table. In other words, you could do a free body diagram of this structure here, left completely intact and merely isolated from these pins right here. A legit free body diagram. And actually a solvable free body diagram. Now, if you think about this, you might say, well, wait a minute. There would be two unknowns right here and two unknowns right here. That's four unknowns. You're saying I can write one free body diagram and I can solve the four unknowns? No, you can't, Professor. That's BS. Why is it not four unknowns? Look at this one, folks. Look at that problem right there. Everybody, look at it. Ask yourself, why is it not four unknowns? Who sees it? All right, let's go back and remember something. Remember when we talked about, have you seen it? Thank you. Great work. Remember we talked about when we're doing these problems, always look for two force members. Folks, this problem says nothing at all about the weight of these members. So what do we say about the weight?
0.
They're weightless, exactly, they're 0. A two force member is any element that has no weight, has a grand total of 2 pinholes, and no forces applied to it. BD right there is a two force member. Meaning that if you did a free body diagram of this entire thing, isolated merely from these pins, you'd have 2 unknowns right here and 1 unknown right there. You've got 3 unknowns, 3 equations in the budget. You can figure those out all day long, no problem. We're done. Except you weren't asked to figure out what these 2 were. You were asked to figure out what's in pin B. So what does that mean? Well, it means that while you could do the free body diagram of the entire frame, and maybe that's a good idea, You can also do a free body diagram of a whole lot of things, and they're also good ideas. So how about this? What if we just did a free body diagram of that piece by itself? That piece by itself. If we did that, let's see what it looks like. If we did that free body with pinhole here for what is that? That's B. Here's C. Here's where my cable used to be attached here at A. Let's do the usual here. X, Y, standard XY coordinate axis system, right? So now, let's apply forces. No weight, no problem there. But we do have the weight of 2,400 pounds hanging off of point A right here. And as it is with every weight force we are ever going to draw, the directionality of that weight force is always straight down towards the center of the earth, right? So straight down towards the center of the earth, 2,400 pounds. Over here at pin C, we have no idea the directionality of these pin forces, but I don't know, maybe CY goes like that, maybe CX goes like that, right? Who knows? And then we have BD. Now, folks, we have a force here on this pin. We have already asserted that member BD here is a 2-force member, and we all know that the line of action of the force in a 2-force member has to pass along a line that goes through the center of the pinholes, right? So that means the force here at BD is going to be going along here. We don't rightly know just yet the directionality of it, and maybe we don't need to know it, but this is a great example of, but we can know it, right? So think about this, folks. Draw in here. If I pull down on this member right here, if I apply a weight to pull down on this, as this is trying to go down, this is pushing back on it, right? Wouldn't it be true that this member here is trying to compress BD, trying to squeeze it together? It's certainly not trying to pull it apart, right? So it's trying to compress this down. So if the force acting upon BD is compressing it, then the force BD is reacting to on this member must be opposite of that, so it needs to be going outwards like so. So I believe that that would be the correct directionality for BD. What I don't have right now, though, is I don't have the angle. So let's get an angle on this thing. I need an angle right here. I see my triangle, just like that. I see the height of the triangle according to that dimension right there is 3. I see that the leg here is 5 according to that dimension right there. So if I call this angle theta, then I look at theta and I've got the opposite leg, I got the adjacent leg. So the tangent of theta, opposite over adjacent, is equal to 3 over 5, 0.6, which means that theta, when I work it backwards, is going to be equal to, let's see here, I've got about 30.96 degrees. So, with that said, I know that my angle right here is 30.96 degrees. And folks, I want to step back here. I want you all to really digest what's in front of you here. And as you're digesting it, keep asking yourself, did I see anything there that was new? If you look at the free body diagram of this frame piece, we drew an isolated picture of it, of the piece we want to do the free body diagram of. We've showed a XY coordinate axis system. It had no weight, so we didn't have to worry about that. It had one applied force, and that was the 2,400 pounds that was hanging from it. So we showed that. And then we put forces at places where that free body diagram item, that object, used to be in contact with something. And those forces followed every convention we've already seen. Pin force, no problem. X, Y, don't worry about it. Let the math figure out which one's which. We saw the 2-force member, and we applied the 2-force member force, BD. We've seen that before. There is nothing new here. And now, with a complete and accurate, we can check the box, we believe in our free body diagram, we're confident in our free body diagram. Now, it's just equations of equilibrium. Again, in the absolutely nothing new here department. So I got 3 unknowns, let's write 3 equations. So if I sum up my forces in the x direction, what have I got? I've got Cx over there, which is a purely x directional force, and it's going in the positive x direction because I define positive x that way. Again, nothing's new. Cx. That's a y force. That's a y force. That's not in the picture. But BD over here has got a x component. In fact, it's going to be BD times the cosine of 30.96, and it's going in the negative x direction. So minus BD cosine 30.96, and that's going to be equal to 0. One equation, two unknowns, can't do anything with it. But let's go now to the sum of forces in the y direction. So as I sum forces in the y direction, I see Cy up here, going in the positive y direction. I see that BD is tending towards positive y, so its y component is going to be positive BD times the sine of 30.96. And then I got this one right here. The 2400 is going in a purely negative direction, so minus 2400. And that took care of all those, so they're going to add up to 0. And then finally, folks, if you're keeping track here, 1, 2, now 3 unknowns. 3 unknowns, 2 equations, no problem. Let's some moments about something. Let's remind ourselves that counterclockwise is our positive moment. This just comes down to, well, which place do you want to use? Take a moment to ask yourself, where would you write your moment equation, right? And knowing that every answer is right, but where would you do it? Me, I'm liking point B. Because think about this, if I choose point B, then I don't have to worry about BD at all. I don't have to worry about CX, it's passing right through point B. So my moment equation is going to have CY and 2400 in it. That's easy. So let's do it about B. And again, no contribution from BD, no contribution from CX. CY over here, because where B is, CY is going to be causing it counterclockwise, so it's going to be CY, that's positive, times the moment arm here. So the distance from B over to here, we're given as 5. So CY times 5. And then I got this 2400 over here. So this 2400, with respect again to point B right here, is doing a counterclockwise. So that's going to be positive. So plus 2400 times its moment arm, which is the distance from here over to here, which is also 5. And that's going to be equal to 0. So immediately, we see from that moment equation that we can solve for Cy. In fact, when I move this term over to the other side of the equal sign, it's going to become negative. So I'm going to end up with Cy equals minus 2400. Now, folks, I could write down times 5 divided by 5. We all know what that's going to lead to. So Cy is going to be equal to negative 2400 pounds. Meaning what? Meaning, well, A, that's equal to negative 2400. B, or it's equal to 2400 magnitude-wise, and that we assumed that the directionality was pointing up, when in fact the directionality is pointing down. So, no big deal. But now with that, I can come into this equation right here. If I plug in my Cy here, which is negative 2400, so notice here, folks, this is important. That's listed here as positive Cy, but the value of Cy that we calculate is negative 2400, so we got to carry that through our math, right? So I'm going to have minus 2400 plus BD sine 30.96 minus 2400, minus another 2400, is going to be equal to 0, which means that BD, therefore, is going to be, when I move that to the other side of the equal sign, it's going to become positive, so will that one, so they're going to add together. So I have 4,800 divided by the sine of 30.96. And folks, if you plug that in and crank that out, you're going to end up with BD being equal to, I get about 9,330 pounds. And very importantly, folks, that one worked out to be positive, which is no surprise. Before we ever went into the math, we already surmised that BD had to be pointing that way because it's the reaction to what would otherwise be a compressive force on BD. So we thought the directionality was right, and our math has confirmed that for us. So now we got that one. And then, folks, once we've got BD solved, we can solve for this one right here. If I bring this over here, now I'm going to have CX is equal then to BD cosine 30.96 and we know that BD is, as we just figured out, say is 9330. And folks, plug it in, crank it out, you're gonna end up with CX being about 8,001 pounds. So now, we know what CX is, we know what CY is, and of course we know what BD is. Here's the only thing remaining on this one. It's just a reminder that we always have to pay attention to the narrative. The narrative told us to determine the magnitude of the pin reactions at B and C. So if I want to get the magnitude of those, the magnitude of C then is going to be equal to the square root of CX squared plus CY squared. Again, hearkening all the way back to stuff we looked at back in chapter 1. Which is going to be therefore equal to the square root of, what do we say for CX? I think we said, yeah, 8,001. So 8001 squared plus CY, we got is negative 2,400, so minus 2400. But when we square that, that's going to become positive anyway. And if we plug that in, crank that out, folks, we end up with C being equal to, the magnitude of C is 8,353 pounds. And what should be fairly obvious is the magnitude of BD is already known. Since BD here is a non-XY force, it's just a singular force, we know the value of BD was 9,330 pounds, which means the magnitude of BD is 9,330 pounds. And that's it. That's the problem. Now, well, first of all, does anybody have any questions about what you just saw there? Questions, anybody on this one? Don't hesitate if you got them. Here's my hope. My hope is that everybody in the room right now is able to look at this and say, you just didn't show me anything new at all. You showed nothing new here. What'd we do? We started off with a problem. We have a picture of it. We have a narrative. There's an ask. We figured out some angles. Well, boy, there's nothing new there, is there, right? And then we said, all right, we're trying to figure out something here, and we kind of went through a little exercise of what's the right thing to make the free body diagram of, knowing that we could have picked anything, and that anything may have led us nowhere. And if it did, then we just picked something else, right? So in this case, though, we realized that, hey, you know what? One free body diagram of that piece right there, because we recognize that two-force member, solves this problem. So what did we do? We drew a free body diagram. Once we were confident in our free body diagram, and man, I can't emphasize that enough. You don't do anything until you're confident in your free body diagram. When you really believe my free body diagram is right, then and only then do we just go and do the same old, write some equations of equilibrium, knock them out, solve the problem. Just like I said at the very beginning of this course is all about drawing pictures. This is the key, folks. This stuff down here, whatever, anybody can do that. This is the key. But there was nothing new here that we saw in leading to solving this problem. Once again, any questions about this one, anybody? Yeah.
So to find B, we just do BD times cosine squared, square root of BD times cosine 30.96 plus BD sine 30.96 squared.
I want to make sure I understood your question, right? I think you were asking if I didn't know BD, right? Is that what you're asking?
I was asking, like, because it wants you to find the reactions at B and C, and I only see it for C.
So when we did, let's focus on C first. We solved for C, Y, and CX, right?
Yeah.
We got that through our equations. And then we said, okay, the pin reaction, which is the combination of these two, we did here, and we got the combination being 8353, right?
That would be that more of a diagonal line. So
Exactly.
BD out there.
Exactly. In fact, it would be a diagonal line in this case here of, since we know CX is going back this way, so CX is really going this way, right? It would be a diagonal line going back like this, basically. But that's how we would get that. With B, knowing force BD, and it doesn't have a Y component, we didn't solve for a Y component and X component, we skipped that whole step because BD is the magnitude of the force in that pin. So it gets us there. But it's a great question. Thank you for asking that. I thought I saw another hand flinch somewhere. Was there another question somewhere? Anybody? Okay, good. Let's keep up the parade of, you're not seeing anything new here. One more problem, and then we'll wrap for the day. Now, folks, after I get this up and we talk about what we're being asked to figure out, I'm going to take a minute here. I'm going to ask you to just draw the free body diagrams or make note of the free body diagrams that you think need to be done here to solve this problem. So here's the narrative on this one here, folks. Let's focus on the narrative first, because we see in this narrative great similarity to what we just saw in the previous one too. The narrative here is just asking us one thing and one thing only. We're asked to determine the magnitude of the pin force at B. So I got a pin down here at B. I want to know the magnitude of that force. That's all I'm asked. Now, note the frame here, folks. The frame comprises this upside down L-shaped bracket right here. We've got a quarter circle bracket over here between O and A. We're showing the radius on that, by the way, is 0.4 meters. And check out, the only applied force here, folks, is actually an applied moment. In other words, imagine if you had like a bolt head here, for example, and you got a wrench on this and you're trying to twist that wrench, you're applying a moment to this. That's the only thing that's being applied. Now, to you all, take a moment here and just ask yourselves, or jot down if you want to, what would you draw? If you were going to attack this right now, what would you choose as your free body diagram, folks? And I will tell you, one free body diagram gets the job done on this one. So take a moment, just think about it. If you noticed that bracket OA is a 2-force member, then this becomes obvious. So look at OA one more time, folks. Again, no weight, a grand total of 2 pinholes, and no applied forces. That's a 2-force member, right? So we look for 2-force members. In view of that, The free body diagram that we want to create is of the upside down L-shaped bracket. Again, now we can draw other free body diagrams and we'll get there. In fact, here's something worth thinking about, folks. If you didn't recognize that member OA was a 2-force member, question, does that doom you to not being able to solve the problem? Not at all. All it means is you got one more unknown than you would otherwise have, which means you got to write an extra free body diagram to solve the problem, right? We still solve it, it's just more work. But if I do the upside down bracket, I'm going to use my same XY coordinate axis system here, because I'm tired of writing that down. I'm going to come down here, and first of all, this is not a 2-force member. Why? Because it has an applied force. So we have an applied here, right in the middle of this thing, by the way. We've got an applied moment here of 200 Newton meters, got that, so not a 2-force member. We have BX, we've got BY. Do we know their directionalities? Nope. Do we care? Nope. So maybe BX is going that way, maybe BY is going this way. Remember, all we're being asked to do is figure out the magnitude of the pin force at B. Hey, here's one for you. If all I care about is the magnitude at force B right here, do I really need to worry about the force up here? Oh God, take all of 1/2 of a second and say, of course you do. That's not a complete free body diagram. We don't do anything until our free body diagram is complete. So in this case here, folks, all right, what are we looking at here? Well, we've got a force up here on OA. Do we really know its directionality? Yes, but do we need to? No. How do I know the directionality? We'll think about this. If I really did apply this counterclockwise torque to this, that means this thing is going to try to bend this bracket here this way, meaning it's trying to compress OA, meaning that OA is pushing back for the exact same reasons we just talked about a little while ago. So I'm going to have a force here, let's call it force OA. And by the way, because of the fact that this is a quarter circle, right, and I'm connecting the lines between the two pinholes right here, so this distance here and this distance here are the same, which means that line is on a 45-degree angle. So because of that, I know this is a 45 right here, 45 degrees. Folks, step back, look at that free body diagram, and ask yourself, is that free body diagram complete? Just go through the checklist. Did you draw an isolated sketch? Yup. Do you have a coordinate axis system? Yup. Did you include the weight if known? Yeah, it was 0. Did you include the applied forces? Yes. Do you have a force representation at every place that this thing used to be in contact with something? Yes here, yes here, complete free body diagram. Now, with that said, and again, once you are confident you've got the complete free body diagram, now we go to the equations of equilibrium. We're wanting to figure out what BX and BY are, and I'm asking myself, is there any way to do this with just one equation? The answer is no, because we got to figure out 2 things anyway. So, all right, no problem. Let's sum forces in the x direction. So if I do that, OA here is tending towards positive x, so it's going to be OA cosine 45 plus BX, and that's going to be equal to 0. BY is purely y directional, can't do anything with it. Hey, shouldn't that 200 be here, maybe, like, because it's a force, right? No, it's not. That's a moment. So that's a moment. It would never, ever show up in a force equation. So I'm done with the force equation there. Now let's sum force in the y direction. I'm going to have OA sine 45. BX is not in that picture, but minus BY here is. BY tending towards the negative in this case, so minus BY. And once again, that's the only y-directional force I've got. The 200 doesn't show up there, so 0. Now, let's sum moments about some place. And counterclockwise is always positive moment. Question becomes here again, where, right? Every place is the right answer. I don't know if there's tremendous value in doing it like at point A versus point B, but let's do point B, so we got an equation with only one unknown in it. So I'm going to sum my moments about B. And so where do I go from there? So okay, OA, now I'm thinking Brignon's theorem. OA, I resolve it into its components. So here's OA cosine 45. Here's OA sine 45. Notice how quick we're just resolving this now, folks. Well, hopefully we're at the point we're not even thinking about this stuff anymore. So I've resolved that into its components. There's what I've got. So now if I'm doing my moments about B, then I know that BY is not in that picture, BX is not in that picture, but OA cosine 45 right here, that, with respect to B, is doing a big clockwise, so it's going to be negative. So I'm going to have minus OA cosine 45 times its moment arm, which would be the distance from its line of action down to point B, which from way over there in our original diagram, the dimensions, we see this distance here is 0.8 meters. So let's simply multiply by 0.8. That takes care of that one. Then I got OA sine 45. Easy to see if I slide it down along its line of action. Easy to see that this one's also doing a clockwise. So therefore minus. So minus OA sine 45 times its moment arm. This distance from its line of action over to here, which from our original diagram is 0.6. Got that. And then I've got the 200 Newton meter force that's applied right there. That is a moment, so it goes in the moment equation, right? It's an applied moment, so it's in the moment equation. As drawn, we see that this is doing a counterclockwise, so therefore it's positive, so plus 200. Do I need to multiply it by any distance? No, because it's already a moment. All right? The mistake that's just waiting for you to make it is say, oh, well, that's 200 times 0.4. No, it's not. It's already a moment, so you don't need to multiply it by anything. Remember, a moment by definition is a force times a distance. This is already a moment for us, so just simply plus 200. That's it. And so I've taken care of this force, and that moment. These two are not in the picture. There's that equation. Set it equal to 0. And folks, as you look at that right now, you should be able to see that we've got the ability to solve for OA here. In fact, if we do this, and I'm just gonna, let's see if I can plug this all and crank this out. So if we do this, folks, these two items here, when they go to the other side of the equal sign, are gonna become positive. So I'm gonna have OA times, let's see, both of these are 0.707, so OA times 0.707 times 0.8 plus 0.6. Now, folks, think about this. 0.8 plus 0.6 is 1.4. 1.4 exactly. 1.4 times 0.707 is real close to 1. This whole thing, by the way, is going to be equal to 200 here. So this is almost 1. It's like 0.99 if I were, yeah, 0.99. So OA ends up being then 200 divided by 0.99, which is equal to 202. So 202 newtons. And worth noting, it worked out exactly positive, so our assumption about its directionality is correct. But now that I know that, I can solve for Bx. So Bx is going to be equal to, according to this equation right here, minus OA cosine 45. If you plug that in and crank that out, you're going to get Bx is equal then to minus 143 minus 143 newtons. All that means, folks, is we assume Bx is going that way. In reality, Bx is going to the left. And then if we plug it in right here for By, check this out, By is also going to be, in this case, OA times the sine of 45, which means it's going to work out positive. We guessed right on By, and that's also 143 newtons. So we have solved now for the components, but we go back over to the original problem. It asks us to determine the magnitude of the pin force here. So in this case, the magnitude of B is going to be nothing more than the square root of Bx squared plus By squared. So 143 squared, yeah, let's treat this one as the negative one, so it doesn't matter. So negative 143 squared, which becomes positive, plus 143 squared. If I plug that in and crank that out, folks, get this, B is equal to 202 newtons. And that is that. In fact, it is worth noting here, folks, that it's not a surprise that B ended up being the same as the force in OA at 202 newtons, because if you think about it, some forces in the system, they got to be equal. So the magnitude of B would have had to been the same as the magnitude of OA. So we actually had a safety check in there built in. We didn't even realize it. But one more time here, folks, just to put the punctuation on it. Now we're working on frames. What's changed here? Nothing. we're still drawing pictures, we're still doing free body diagrams, and with good free body diagrams, we're using equations of equilibrium and knocking out these problems. It's gonna start moving fast now, folks, because we already know everything we need to know to solve problems like this. Questions on this one, anybody? Yeah, fire away.
So when we're given a moment that's like already being applied, it's already new meters, we don't need to multiply it by the distance?
Correct, that's exactly right.
So like any point?
It doesn't matter, and it's a great, I'm so glad you asked the question, folks. So I want to double check that question. The question is it just goes again, so you're saying you don't need to multiply this by any distance, and part of the reason for the answer to that is because it is already a moment, but let's think about it in terms of effect on the system. Moments, because of rigid body mechanics, means if I apply a 200 Newton meter moment here, I would have the same thing if I applied it right here, the same effect on the system, or if I applied it right here, or if I applied it right there. It doesn't make a bit of difference. So yeah, when we are given a moment, and this is one of those, just so we all hear this, this is one of those that is so easy, we actually sometimes don't want to believe it's that easy, right? It's like, no, come on, we're engineers, it's got to be harder than that, right? It's not. When you see a moment, it's nothing more than you're going to put that moment in the moment equation exactly as it is. The only thing you got to worry about is it clockwise or counterclockwise. That's entirely it. Thank you for that question. Yeah, fire away.
Regarding the midterms, you said, this question, if you didn't recognize OA as a two-force member, it would have made the problem just a little harder with another free body diagram.
Yeah.
Would we be penalized for that in the midterm?
No. It's a great question. I want to make sure everybody heard it. So the question, and I'm going to summarize it, the gist of the question was, hey, what if I did this problem? What if I gave you this problem in the midterm, and you didn't recognize this as a two-force member, so you just did some extra free body diagrams and you still got it anyway? There's no penalty for that. I might put a little note on there, hey, that was a two-force member, you know? It could have been easier, but no penalty, none at all. Good question, and thank you for that. What other questions you guys got? Okay. Go have a good rest of the day. See you guys on Thursday, and we will pick up on Thursday into machines. Be ready to ask questions about the midterm.